Okay, so this is the last of the exercises that we've completed in class, and this one's probably the hardest of all the ones that we've done. The most important thing to recognize first is what the dip of the different beds in there are. So here we have some beds that have strike and dips marked on them. These ones are going at 75 degrees. I think that's the slate unit. Let me grab the notes. Yes, that one there is the slate. So we've got the strike and dips of the slate. So now we need to figure out what the strikes and dips on the other units on this map are. Now we've got these guys up here that are all the boundaries here, they're all parallel to each other. So we've got this one going around like that, got one going around like that, this one going around like that, this one like that. You'll notice that they're all parallel to each other, and the other thing that they're parallel to are the contour lines, which are dashed around. So here we have our contour lines dashed around like that, one around there, one around there. So we've got unit boundaries that are parallel to contour lines. So what does that mean? Well, hopefully you remember from last week, that means that these are all sitting horizontal. So these are horizontal layers. So we can put a plus on there if we felt like it. We know that these are all sitting flat lying like that. These ones are dipping at 75 degrees. So that leaves us with a couple of units, or actually first let's just note, a lot of people miss this. This guy here, this is a contour line, and this boundary here is parallel to that contour line. So again, this unit here is flat lying, and I'll come back to that guy a little bit later. Now this thing in here with these stripes and dots on it, if we look on our key, this one here is labelled as the diorite. Now diorite, hopefully you remember from the igneous lectures, that is an intrusive rock. So it won't have strikes and dips on the beds. It doesn't have beds. You don't have beds in these intrusive igneous rocks. So now we figured out these guys in here are horizontal. These ones are dipping at 75 degrees. This one is also horizontal. This has no strikes and dips on it. So that just leaves us with this guy here, this black thing, the dolerite. That is also an intrusive rock, but we know that this is striking horizontally, so it's going like, oh, sorry, not horizontally, vertically. It's going like that. So it's going through our beds like that. And we know that because it's cutting in a straight line straight across this topography. The horizontal beds will always follow the topography. The vertical beds always cut straight across it in straight lines like this. So this is a typical fill pattern of a vertical rock. So this is going up, straight up and down, not horizontally like the others, and not dipping like these guys. So we've now figured out the strikes and dips for all our different rocks. So what do we do now? Well, of course, the first thing we do is we've got topography on here, line up our piece of paper along there, put our tick marks where we've got these topographic contours. A lot of people forget that this is the first thing you do. It's actually quite an easy thing to do. It's something you probably did in high school. Draw your topographic profile. And I think this is roughly what the topographic profile looks like. So again, we've got our map scale here, 1 centimeter to 100 meters. That's what I've drawn here. These are 1 centimeter apart, 1 centimeter for our 100 meters. So I've kept the vertical and the horizontal scale the same. So we could write BE equals 1, just like I've done with all the other geological cross sections so far. So we've done that. We've got our topographic profile on. The next thing we do is, once again, we line up our piece of paper along there, put our tick marks, so we've got our geological boundaries. Again, mark those down like this. The easiest ones to put in first are either probably this vertical guy. It's probably the easiest one to put in first, so that's what I did. I put that in first. So this is our dolerite. This is a dike. If you remember back to the igneous lecture that I gave on Wednesday this week, we talked about what dikes are. This is a dike. Then put on our nice flat lying units, these guys here. And again, keep yours a lot neater than I've done. I've kept mine pretty rough, but you guys should be keeping these as neat as possible. This dike cross cuts this unit. So make sure you have that drawn in, make sure that's solid through there, and cross cuts that unit there. So we've got all of those in. Next thing we can do is put in our slate, and our slate is going down at 75 degrees. In fact, ideally what we really should do is, if we look at this cross-section line like that, it's actually not perpendicular to the strike of this slate, which is like that. I'll try and draw that a little better. So that is our cross-section line. Our slate perpendicular to our strike of our slate is like that. So again, really we need our Woolnough diagram. We need to measure this angle in here, which I think I did measure, and it was 32 degrees roughly when I measured it. And then you need your Woolnough diagram, and you will put your line down the direction, the angle of direction down at 32 degrees, and then your true dip, which is this 75 here, so you put it across at 75, and where those intersect, you look at the curves that are coming down like that. And from memory, this intersected somewhere between the 70 degree curve and the 75 degree curve, and it was roughly halfway between the two. So I think the angle that I've actually drawn in here was 72 degrees. So not a big difference again, but it is important to try and keep these as accurate as possible. So to draw this unit in, we need to figure out where it starts on the ground. So the way I've done this, and the way I'm happy for you guys to do that, is simply to join these dots where we can't see this slate unit. So the slate unit is underground here, still exists, it doesn't disappear just because there's stuff on top of it, it's just underground. So I just joined those two dots. There are more accurate ways of actually figuring out exactly where it sits along this line, but we're not going to go into those in this course. So if you just want to estimate it and say that it sits somewhere like that, and then you have your piece of paper lying along, draw your point there, which I think is where I've drawn this point here. So that is your slate. You use your protractor, and again you're measuring to the horizontal, you're measuring 72 degrees. Put my dot down there somewhere using my protractor, and then you draw your line down along like that, and that gives you your slate. Somewhere over here is going to be our limit of knowledge. This slate unit is relatively thick. We can see that from the map. We can see that it's a relatively thick sort of unit. So our limit of knowledge is somewhere over here. So it's a relatively thick thing, so put it over like this, and we don't really know what's going on over here. I've drawn this. This was actually a mistake. You can ignore that altogether. This stuff here is the diorite, so this is an intrusive rock. This is an unconformity along here, and technically this is what we would call a non-conformity, where we have a bedded unit sitting on an unbedded unit. Remember, igneous rocks don't have any bedding, so this line along here is an unconformity, or a non-conformity is the technical type. This is also an unconformity along here. In this case we've got an angular unconformity, because you've got that 72 degrees there, and this stuff is sitting flat, so that's another unconformity on this map. Now the last thing is this stuff in here, which is parallel to bedding, parallel to the contour intervals, and that's been labelled as alluvium on the key. So alluvium, that's a U. Alluvium. Alluvium is basically dirt on top. It's really just the soil, the transported regolith. It's sitting flat. I've just kind of thickened up this line here. It's probably actually relatively thin. It might only be 1 to maybe 10 meters in thickness. We don't know exactly how thick it is here, but this is going to be very modern material. It's basically the stuff that's washed down the hill and has ended up being deposited at the base of the hill. It's just the transported regolith. So you don't actually need to draw a unit really in there. In fact, you can ignore it altogether on your cross sections, probably the better thing to do. So that's that one. So next thing, I was going to go quickly through the geological history of this map, because this one's a little bit more complex than any of the others that you've seen. So the first thing that's happened in this area is we've deposited mud. Mud is the protolith of slate. You guys might not have known that yet. You'll learn a little bit about that in Luke's metamorphic lectures. If you had simply wrote slate protolith, that's fine. Protolith means the stuff that was there before the metamorphism happened. Remember, slate is a metamorphic rock. Something had to exist to be metamorphosed to form that slate. And in slate's case, it's actually mudstone that gets metamorphosed. So you had mud deposited, which was then buried and lithified. Lithified means turning into rock. It was tilted and metamorphosed. So this is where it turned into that slate. So it turned to slate there. Then you had your diorite intrusion. Remember, the slate had to exist, or at least the mudstone had to exist before that was intruded. You had to have something there to be intruded. You had to have some kind of host rock there that was present before the intrusion could form. You can't form an intrusion in the middle of the air. You have to have a rock there first. So the stuff that was there first was the slate. Now these two guys, it's actually ambiguous. One of those may have occurred before the others. We actually can't tell. So if you had these the other way around, I wouldn't mind. I mean, you can't actually tell whether the tilting and metamorphism happened before the intrusion or the other way around. So this material, all of this stuff, was then uplifted and eroded to a flat surface. So you've had this stuff brought back up to the surface of the Earth, eroded it flat, and then on top of that you've deposited these units here, these flat-lying units. So you've erupted a dacitic ignimbrite. This is a volcanic rock. We'll talk a little bit about ignimbrites in my volcanics lecture next week. You've had the intrusion of the dolerite. Now this dolerite has intruded. It cross-cuts this unit only, the dacitic ignimbrite. It doesn't actually cross-cut any of the other units on your map. So that's come next. Then you have the basalt erupted. That's this unit here. These dolerites and basalts are identical in composition. So this was actually probably the neck that fed the volcano out of which these basalts flowed. So these two actually might be have formed simultaneously. Now we don't know that exactly, but that is a possible hypothesis that this and the basalt formed at the same time. On top of the basalt, we had sand deposited. On top of that, you had gravel deposited. These guys were then all buried and once again lithified, so turned into rock. So that turned our sand into sandstone, it turned our gravel into conglomerate. Then this material was uplifted and eroded, and then we have the alluvium deposited and continual erosion to the present day land surface. So that is the geological history of this area. So hopefully you got all of those points. So I hope this helps you understand your first part of your case study. If there are any questions, again, the forums are the best place to ask. I'd encourage you guys to talk about these exercises so you can help out each other a little bit as well. If you get really stuck, you're always free to email me. Okay, thanks guys. I'll see you in the next class.